Welcome back to the channel. Today we are travelling deep into Earth's past to a time when summer seemed to last for millions of years and the planet reached some of the hottest conditions in its history. If you enjoy these science journeys through ancient worlds and cosmic mysteries, please remember to like the video, subscribe and share it with a friend who loves this kind of content. It really helps the channel grow. Thank you so much for being here and spending your time with this documentary. The long Cretaceous summer begins as a world already warmed by deep time settles into a new and less stable balance. 100 million years ago, during the early part of the late Cretaceous Earth, orbits the Sun much as it does today, yet the surface conditions are markedly different. There are no polar ice caps. Sea level stands far higher than in the present, flooding wide continental shelves and pushing shallow warm seas far inland. Global temperatures sit many degrees above modern averages, and mid-latitude oceans feel more like large heated pools than the cooler waters familiar to human experience. In this world, forests reach almost to the poles, and humid air moves slowly over extensive lowlands that are broken not by high mountain chains, but by broad plains and gentle uplifts. The climate is already greenhouse-like, but the long summer has not yet reached its peak. It is in this setting that the event later called the Cretaceous thermal maximum begins to take shape. At this stage, the pattern looks at first glance like an exaggeration of what is already there. Dinosaurs of many kinds dominate the land. Giant sauropods move through conifer-rich forests and fern-filled openings. Large carnivorous theropods patrol river valleys and coastal floodplains. In the seas, ancient lineages of marine reptiles, including ichthyosaurs and large long-necked hunters, still occupy major ecological roles. The air itself carries a higher concentration of carbon dioxide than in the modern atmosphere, and the greenhouse effect that results helps keep nights warm even at high latitudes. This is not a marginal environment for life. It is a world filled with vegetation and complex food webs. Yet subtle signals indicate that the system is drifting toward a more extreme state. Some of these signals are geological. At the bottom of ancient oceans, layers of fine sediment begin to record changes in chemistry and temperature that later scientists will decode with mass spectrometers and microscopes. Ratios of oxygen isotopes in the shells of tiny plankton shift in a way that points toward rising sea surface temperatures. Carbon isotopes trace alterations in the global carbon cycle, hinting at increased input of carbon from volcanic sources or from the breakdown of buried organic matter. On land, the arrangement of continents and growing ocean basins sets the stage for a redistribution of heat and moisture. The supercontinent that once gathered most land into a single mass has already broken apart. Between what will become Africa and South America, and between North America and Eurasia, the young Atlantic Ocean continues to widen. Along the mid-ocean ridges and rift zones that crisscross this growing basin, magma rises and cools, forming new crust and releasing gases into the water and air. This volcanic activity is not unusual for Earth on geological timescales, but during this interval, the combined effect of extended seafloor, spreading large igneous provinces, and persistent tectonic reshaping appears to push the background greenhouse conditions into a more intense regime. The result is a slow but steady addition of carbon dioxide to the atmosphere and the upper ocean. Because climate responds to such changes over thousands to hundreds of thousands of years, no single year or decade stands out from within the Cretaceous itself. Local ecosystems adapt and reassemble. Species ranges expand toward the poles. In many regions, plant growth flourishes, supported by warm temperatures and high carbon dioxide, which can enhance photosynthesis. Forests spread over high-latitude continents, creating environments where large herbivorous dinosaurs browse beneath long summer daylight, even as winter nights remain relatively mild. From the standpoint of life existing in that time, the world seems simply warm wet in some places and seasonally dry in others. From the standpoint of distant observers reconstructing it from fossils and rock cores, however, a pattern emerges of steadily rising temperatures and deepening ocean stratification. One key feature of this evolving climate is its unevenness. Regions that are already humid tend to become even wetter. Monsoon-like systems strengthen over some continents, feeding large river networks that meander across low-gradient floodplains. In other regions, especially in the subtropics, high-pressure systems stabilize and suppress rainfall, extending belts of aridity and creating expansive semi-arid landscapes. The contrast between wet and dry zones sharpens, setting up sharper ecological boundaries and influencing where different dinosaur faunas and plant communities can thrive. As the long Cretaceous summer builds, the oceans act as both heat reservoir and transport system. Warm surface waters move from the tropics toward higher latitudes, releasing heat to the air and helping to maintain relatively small temperature differences between equator and poles. At depth, however, circulation becomes more sluggish as density contrasts weaken and oxygen-poor waters expand. This slow rearrangement of currents is invisible to observers on the surface, yet it is crucial in shaping what will follow. It determines where nutrients upwell, where oxygen is replenished, and where large marine organisms can find stable refuge. In this early phase of the long summer, the system still holds many of its older inhabitants. Ichthyosaurs, though already in decline compared with their earlier dominance, remain part of marine ecosystems. Large pliosaurs and other apex marine predators still occupy the top of food chains in several basins. On land, there is no sign that giant sauropods are nearing the end of their evolutionary story. If anything, some lineages are trending toward even larger body sizes supported by abundant plant biomass and warm climates that reduce the energetic cost of maintaining large bodies. The apparent stability is deceptive. When scientists in the present day examine the rock record from this interval, they do not see a single sudden boundary so much as a slow ramp toward a hotter state that will eventually push the climate beyond thresholds that many ancient lineages can tolerate. The first section of this story therefore rests on a paradoxical image. Earth is comfortable for the life of its time, yet measurements preserved in stone reveal that key variables are being nudged in a single direction. Carbon enters the system faster than it is removed. Sea level continues to rise. Forests advance into regions that were once cooler. Polar climates, rather than acting as cold anchors, become mild extensions of a near-global temperate to subtropical band. The long Cretaceous summer does not begin with an abrupt switch. It begins with a quiet persistence of processes that have been at work for millions of years, now entering a phase where their combined effect will make this one of the hottest sustained periods in at least 200 million years. As the long Cretaceous summer gathers strength, the deep cause of its heat lies not in the sky, but in the slow rearrangement of rock far below the oceans. The supercontinent that once unified most land on Earth has already broken into large drifting pieces, and among the most important of these new features is the young Atlantic Ocean. Where there was once a continuous span of crust connecting the lands that will become North America, South America, Africa, and Europe, there is now a widening basin filled with seawater. The line along which this basin opens is marked by a mid-ocean ridge, an underwater mountain chain, where molten rock from the mantle rises, cools, and forms new oceanic crust. Each increment of spreading at this ridge is small on human timescales, but over millions of years the result is a broad belt of hot, buoyant crust and a continuous release of heat and gases. Modern scientists reconstruct this process from magnetic patterns frozen into seafloor rocks and from the ages of sediments that drape them. The picture that emerges for the mid-Cretaceous is one of especially vigorous seafloor spreading in several ocean basins, including the Atlantic. Faster spreading means more ridge length at high temperature and a larger area of elevated seafloor, that displaces water upward, contributing directly to global sea level rise. It also means more volcanic outgassing along the ridge and at associated hotspots and plate boundaries. The gases released include water vapour and carbon dioxide, both greenhouse agents, but it is the long-lived carbon dioxide that matters most for climate over these spans of time. As magma degasses beneath the young Atlantic, this carbon enters the ocean and then equilibrates with the atmosphere, gradually thickening the blanket of greenhouse gases that surrounds the planet. The opening of the Atlantic does not act alone. In roughly the same broad interval, Earth experiences episodes of intense volcanism that build large igneous provinces on the seafloor and on the edges of continents. One example lies in what will later be known as the Caribbean region, where vast accumulations of basalt mark a period of unusually high magma production. Other regions show similar signatures. Together, these volcanic events add more carbon dioxide to the global system, while also changing the chemistry of the oceans by delivering metals and nutrients. When present-day geochemists measure the carbon content and isotopic composition of rocks formed, at this time they see shifts consistent with large inputs of volcanic carbon superimposed on the ongoing recycling of organic matter. The result is an atmosphere whose carbon dioxide concentration climbs well beyond pre-industrial values, known from recent Earth history, perhaps reaching levels several times higher. The exact number remains uncertain, but the direction is clear. More greenhouse gas means stronger retention of outgoing infrared radiation and higher equilibrium temperatures at the surface. As the Atlantic widens, it also creates new pathways for water movement. Before its birth, heat can flow across the face of the supercontinent mainly through the atmosphere. Afterward, the new ocean connects tropical and higher latitude waters in ways that are not simple to predict. Warm surface currents begin to move along the margins of continents, redistributing heat and moisture. Yet the deeper circulation appears to grow more sluggish. In a cooler world with strong temperature contrast between poles and equator, dense cold water forms at high latitudes and sinks, driving a vigorous overturning loop. In the mid-Cretaceous, with polar regions already mild and ice-free, that contrast weakens. Warmer high-latitude seas mean that deep waters may form less readily, and the deep ocean becomes more stratified. In such a state, oxygen from the surface mixes downward more slowly, and regions of low oxygen can expand. Sediment cores drilled from what used to be Cretaceous seafloors show dark organic rich layers, deposited during intervals of especially poor deep water ventilation. These layers record episodes known as oceanic anoxic events, when parts of the ocean interior become depleted in oxygen, and conditions change for many marine organisms. The strongest of these events in the late Cretaceous clusters around the time when the thermal maximum is developing, linking the internal dynamics of the Atlantic and its neighbouring basins to the broader pattern of climate stress. Sea level responds in tandem with these tectonic and thermal changes. Young hot oceanic crust sits higher than older cooler crust, lifting broad regions of seafloor closer to the surface. Combined with the absence of large continental ice sheets, this effect raises global sea level to heights far above those of the present day. Estimates suggest that at the peak, average sea level may stand hundreds of meters above modern values. The exact figure is difficult to pin down, but the geological record on land and under shallow seas is consistent with extraordinary flooding of continental margins. Low-lying areas that are now coastal plains become submerged under shallow epicontinental seas. In what will one day be North America, an interior seaway stretches from the Arctic region to the Gulf region, dividing the continent into eastern and western land masses. In other parts of the world, similar flooded zones appear, producing a geography of peninsulas, island chains, and broad inland bays. This configuration increases the area of warm, shallow water that can exchange heat and moisture with the atmosphere. It also shapes the distribution of ecosystems because many coastal and terrestrial habitats are compressed against the edges of rising seas. From the perspective of later analysis, it is notable how several factors align. A period of rapid seafloor spreading coincides with large igneous provinces, elevated carbon dioxide, high sea levels, and a restructured ocean circulation. Any one of these could influence climate. Acting together, they create a planetary state that is not only warm but also dynamically distinct from cooler intervals. The Atlantic Basin in particular behaves as a new engine in the global system. It is born small, yet by the time of the Cretaceous thermal maximum, it has grown to a scale where its currents, chemistry and geometry exert a major influence on how heat is stored and transported. Warm water entering from low latitudes can linger in its broad expanses, while exchange with the deep ocean becomes less direct. Under such conditions, additional carbon and heat delivered to the surface layers are less easily buried or ventilated away. The ocean becomes in a sense heavier with heat. There is also a biological dimension to the Atlantic story. As the basin opens, it creates new coastlines and shallow shelves where marine life can diversify. Coral-like communities, mollusks, and small plankton occupy these waters, and their remains build up thick layers of carbonate sediments. In doing so, they participate in the long-term carbon cycle, drawing carbon from the ocean and atmosphere and locking some of it into rock. However, during the peak of the long summer, the balance between volcanic addition and biological removal appears to tip in favor of addition. Sediment records show intervals where burial of organic carbon increases, but even these strong sinks cannot fully offset the sustained volcanic input. This mismatch contributes to the persistence of high carbon dioxide levels over millions of years. For life living through this interval, adjustments take place gradually. Species shift their ranges along coastlines and through seaways as salinity, temperature, and nutrient patterns change. Some lineages find new niches in the freshly formed Atlantic and similar basins. Others decline as their preferred conditions contract. The eventual disappearance of some long-standing marine reptile groups and the later success of others will be tied in complex ways to the altered architecture of oceans that this basin helps to define. Present-day researchers sometimes comment on how unusual it is to find so many reinforcing processes operating together. A rapidly opening ocean, high seafloor heat flow, extensive volcanism, raised sea levels, and strong greenhouse conditions do not always coincide so neatly in the geological record. The convergence seen in the mid-Cretaceous may partly reflect chance timing in the slow cycles of mantle convection and plate motion. It may also point to feedbacks within the Earth system that tend to cluster such states, because warm climates can alter erosion, sedimentation, and nutrient delivery in ways that influence volcanic and biological carbon sinks. Regardless of the deeper cause, the Atlantic's birth and growth serve as a central structural change that channels the planet toward its hottest known interval in 200 million years. The long summer is therefore not simply an atmospheric phenomenon. It is an expression of a whole planet adjusting to a new tectonic pattern, with the Atlantic Ocean as one of its most significant and enduring products. The atmosphere over this Cretaceous world thickens in ways that would not be obvious to any organism breathing it, yet the physical consequences become unmistakable over geological spans of time. Carbon dioxide, already elevated compared with modern levels, continues to rise as volcanic outgassing and seafloor spreading add carbon faster than weathering and biological burial can remove it. Estimates based on later measurements of ancient minerals and microfossils suggest that concentrations may climb to several thousand parts per million during the peak of this interval, perhaps around the middle of the Turonian stage. The exact values carry uncertainty, but they all point in the same direction: a greenhouse atmosphere strengthened to a rare degree in Earth history. In such an atmosphere, more of the outgoing infrared radiation emitted by the warmed surface is captured and re-radiated back downward, raising the equilibrium temperature at which the planet can balance incoming solar energy. The sun itself is only slightly dimmer than it will be in the far future, so the difference does not lie in the external energy source. It lies in how efficiently the atmosphere and oceans store that energy. As carbon dioxide climbs, the distribution of temperature across the globe changes in a characteristic way. Tropical regions warm, but high latitudes warm even more. This polar amplification, a feature seen in several warm intervals of the geological record, narrows the contrast between equator and poles. Sea surface temperatures in mid-latitude ocean basins, already similar to warm subtropical conditions, by modern standards rise by several more degrees. Reconstructions based on oxygen isotope ratios and other proxies indicate that some of these seas may reach average temperatures comparable to those of present-day tropical lagoons. Polar regions, meanwhile, become temperate or even mild, with ice-free coasts and forests growing at latitudes that now lie within the Arctic and Antarctic circles. Seasonal changes remain because Earth's axis is still tilted, but the difference between summer and winter averages is compressed. Winters are cool and dark, but not deeply cold. Summers are long, bright and warm. Over millions of years, these conditions allow plants and animals to evolve strategies suited to extended growing seasons and less severe cold stress. The strengthened greenhouse also affects the hydrological cycle. Warmer air can hold more water vapor, and in a world without extensive ice sheets, more water is free to circulate between ocean and atmosphere. Evaporation rates from warm seas increase, feeding dense moisture-laden air masses that move inland and rise over continents. Where this air is forced upward by gentle uplifts or by temperature contrasts, it cools and releases heavy rainfall. In some regions, especially those influenced by monsoon-like wind patterns, rainy seasons become more intense. Rivers carry larger sediment loads into the interior seaways, and coastal plains building complex deltas and floodplains. In other regions, particularly under persistent high-pressure zones, descending dry air suppresses cloud formation and precipitation. These areas can become increasingly arid even as the global average humidity rises. The net effect is an amplification of existing wet and dry patterns. Wet zones grow wetter and more flood-prone, while dry zones grow more strongly seasonal or semi-desert-like. A thickening greenhouse and intensified water cycle also work together to reorganize atmospheric circulation. In a cooler world, strong temperature contrasts between equator and poles drive robust jet streams and storm tracks. Under mid-Cretaceous conditions with a flatter temperature gradient, these patterns may weaken or shift. Climate models built on present-day physics but applied to reconstructed Cretaceous geography suggest that storm belts move subtropical high-pressure zones widen, and the paths along which moisture is transported into continental interiors change. The details differ among models, yet they share the conclusion that the atmosphere in this interval is not simply a warmer version of the present. It is dynamically distinct. Weather systems may move more slowly in some regions, leading to longer-lasting rainfall events or prolonged dry spells. Heat waves, in the sense of extended periods of unusually high temperature relative to a regional baseline, should be understood on much longer timescales, because the baseline itself is elevated. For marine life, one of the most important consequences of this atmospheric shift is its impact on ocean stratification and oxygen distribution. Higher surface temperatures make the upper layers of the ocean less dense relative to deeper waters, which are cooled only slowly by limited contact with cold air. The result is a more stable layering of water masses, with less mixing between surface and depth. At the same time, the influx of nutrients from enhanced weathering on land and from volcanic sources stimulates high biological productivity in some surface regions. Plankton blooms capture carbon and form the base of rich food webs, but when these organisms die and sink, their decomposition consumes oxygen in the water column. If the deep ocean does not receive enough fresh oxygen, rich water from the surface, large volumes can become oxygen poor or even anoxic. evidence for such conditions appears in the form of black shales deposited during this time. These are fine-grained dark sediments rich in organic matter, formed in environments where low oxygen prevents the complete decay of sinking biological material. One of the most prominent anoxic episodes in the late Cretaceous coincides with the peak of the thermal maximum. It is recorded in many parts of the world from what are now the Atlantic margins to distant basins. To the organisms living through it, this change unfolds gradually, but in geological terms it is sharp enough to stand out as a global event. In some marine regions, habitats for oxygen-sensitive species shrink or vanish. Species adapted to low oxygen conditions or able to migrate vertically and horizontally to track suitable water masses gain an advantage. These shifts in the physical environment contribute to the decline of some long-established marine reptile groups and create opportunities for others that can tolerate warmer, more stratified, and periodically oxygen-poor seas. The composition of the atmosphere also has more subtle biological effects. Elevated carbon dioxide can enhance the growth of many plants by increasing the efficiency with which they capture carbon during photosynthesis. In the Cretaceous, this likely contributes to the lushness of vegetation in many regions, from fern-dominated understories to conifer and early flowering plant canopies. Greater plant productivity supports large populations of herbivorous dinosaurs and indirectly their predators. But higher carbon dioxide also affects the chemistry of rainwater and soils, making them slightly more acidic and altering the rates at which rocks weather. These changes feed back into the long-term carbon cycle, as weathering of silicate rocks consumes carbon dioxide, while weathering of carbonate rocks releases some forms of carbon back to the ocean. Over very long timescales, such feedbacks tend to limit extremes. In the case of the mid-Cretaceous, however, the balance point at which weathering can match volcanic input appears to lie at a relatively high temperature and carbon dioxide level. This means that the Earth system can remain in a hot state for millions of years before cooling trends reassert themselves. To an observer equipped with modern instruments, this atmosphere would appear unusual but not chaotic. The same physical laws apply. Radiation is absorbed and emitted according to known spectra. Air masses follow pressure gradients and are deflected by planetary rotation. Clouds form rainfalls, winds blow. Yet the boundary conditions are shifted enough that familiar intuitions drawn from recent climates would mislead. Storm tracks occupy different latitudes. The transition between tropical and temperate zones is displaced. Places that are now icy deserts host temperate forests under prolonged daylight in summer. The sense that the world is in a kind of extended warm season with only modest retreat of temperatures in darker months is a natural description of these conditions. This is the origin of the metaphor of a long summer, a period when the planet occupies one side of its climate possibilities for an unusually sustained interval. Modern climate studies sometimes turn to this interval as a natural experiment, a way of understanding how the Earth system behaves under high greenhouse gas concentrations sustained over long times. The Cretaceous thermal maximum shows that such states are possible without any change in the sun's output, and that they involve not just higher temperatures, but a coordinated rearrangement of oceans, atmosphere, and life. It also shows that the transitions into and out of such states can involve thresholds such as the onset of widespread anoxia in the oceans beyond which ecosystems reorganize. In this section of the story, the air itself becomes a central character, not because it behaves unpredictably, but because its composition crosses ranges that are rare in the last 200 million years. In doing so, it locks the planet into a long hot equilibrium from which there is no rapid escape, and from which every living system must find a way to operate or fade. At the height of the long Cretaceous summer sea level stands so high that familiar notions of continental shape would be unrecognizable to a present-day observer. The combined effects of young buoyant oceanic crust thermal expansion of seawater in a warm climate and the absence of large polar ice sheets raised the global ocean surface far above modern reference levels. Reconstructions based on sedimentary rocks, fossil shorelines and subsidence histories suggest that average sea level may exceed modern values by several hundred meters. In practical terms, this means that vast low-lying areas of the continents are submerged beneath shallow epicontinental seas, and the boundaries between land and ocean become diffuse. What were once broad coastal plains turn into chains of islands and peninsulas, while interior basins fill with warm inland waters connected to the open ocean through narrow straits. This rearranged geography is not static. Over millions of years, subtle changes in seafloor spreading rates, mantle temperatures, and sediment loading cause regional sea levels to rise and fall against the general high-stand shifting shorelines, back and forth across continents. Rock records from this time show repeated cycles of transgression and regression, where marine sediments advance over older terrestrial deposits, and then retreat only to advance again. During the peak of the thermal maximum, however, the overall flooded state of the continents reaches an extreme seldom matched in the last many hundreds of millions of years. One of the most striking examples of this drowned landscape lies in what will later become central North America. Here, a broad seaway extends from the northern high-latitude ocean to the southern subtropical waters, effectively dividing the continent into two large land masses. To the west, an arc of highlands and volcanic belts rises along the margin of an active plate boundary. To the east, lower relief terrain grades into the edges of a different ocean basin. Between them lies a shallow, warm and often quiet interior sea. This western interior seaway, as it is later named, hosts rich marine ecosystems and serves as a corridor for the dispersal of species. Along its shores, deltas and coastal plains support diverse dinosaur faunas that adapt to a landscape where marine and terrestrial influences are closely intertwined. Similar flooded regions occur on other continents. Parts of what will become Europe resemble an archipelago of islands surrounded by shallow seas. Northern Africa and adjacent regions host broad coastal embayments. Australia, South America and Asia also display combinations of inland seas and extended continental shelves. The result is a planet whose land surface is fragmented with fewer large uninterrupted interiors and more edges, transitions and semi-isolated basins. This fractured arrangement has important consequences for climate and for life. Shallow epicontinental seas are efficient exchangers of heat and moisture with the atmosphere. Because they are relatively warm and in close contact with land, they can feed strong evaporation, which in turn drives regional precipitation patterns. Air masses passing over these seas pick up moisture and deposit it as rain over neighbouring lowlands and uplands, reinforcing the already intensified hydrological cycle of the greenhouse world. At the same time, shallow waters are sensitive to changes in temperature and salinity. Seasonal variations in river discharge, evaporation and ocean exchange can produce pronounced gradients within these basins. In some regions, restricted circulation and high productivity lead to low oxygen conditions in bottom waters, contributing to the deposition of organic-rich sediments. In others, stronger exchange with the open ocean maintains better ventilation. The patchwork nature of these conditions creates a mosaic of habitats that select for different suites of organisms. Marine reptiles, fish, and invertebrates evolve forms adapted to shallow, turbid, and sometimes variable environments, while terrestrial animals adjust their ranges in response to the shifting coastlines and newly formed barriers. The high stand of sea level also alters the pathways available for migration and dispersal. For many terrestrial species, including dinosaurs, the flooded lowlands and interior seas act as partial barriers isolating populations on different land masses. Over time, this isolation can promote diversification, as genetically separated groups adapt to local climates and vegetation. The fossil record of late Cretaceous dinosaurs shows distinctive regional assemblages, with some lineages confined to particular parts of the world, and others more widely distributed along still connected corridors. For marine species, by contrast, the flooded connections open routes along continental margins and through interior seaways, allowing some pelagic organisms to range widely. The differing effects on land and sea life illustrate how a single physical change such as sea level rise can have opposite consequences for isolation and connectivity, depending on the medium in which organisms move. From a physical standpoint, the near maximum flooding of continents places Earth's surface close to a geometrical constraint. There is a limit to how much water can be lifted onto the land surface through the combination of expanded oceans and flooded shelves, set by the volume of ocean basins and the height of young seafloor. The mid-Cretaceous appears to approach this limit. Some geologists have suggested that during the peak of the thermal, maximum global eustatic sea level reaches one of the highest stands of the entire Phanerozoic eon, the long span of time covering the last several 100 million years of complex life. In this view, the Cretaceous long summer is not only a thermal extreme, but also a near geometric extreme in terms of how much of the continents can be submerged without fundamentally altering the balance between oceans and continents themselves. This adds a further dimension to the sense that the planet is exploring the edges of its typical operating space. The distribution of shallow seas influences not only regional climates, but also the pattern of carbon burial. Organic rich sediments such as the black shales deposited during anoxic episodes often accumulate in these epicontinental settings where restricted circulation and high productivity coexist. When organic matter is buried and preserved rather than fully decomposed, it removes carbon from the short-term cycle and stores it on geological timescales. Over millions of years, this process can act as a negative feedback on high carbon dioxide levels, gradually drawing down atmospheric concentrations. Paradoxically, the same flooded conditions that help sustain the long summer by increasing shallow water area also help set the stage for its eventual moderation by enhancing organic carbon burial. The timing and strength of this feedback, however, depend on the balance between continued volcanic input and burial rates, and during the main phase of the Cretaceous thermal maximum, the system remains locked in a high stand state. The visual impression of the planet from space during this time would be of a world with broad swathes of blue cutting deeply into what are now continental masses, and with relatively narrow bands of exposed land tracing the outlines of mountain belts and stable cratonic cores. Vegetation dots these land bands with greens and browns, while the shallow seas may appear milky or turquoise in some regions due to high plankton content and suspended sediments. Such imagery is speculative, reconstructed from present-day satellite observations of similar environments and from geological evidence, yet it provides an intuitive sense of how different the Cretaceous surface configuration is from the modern one. This altered layout affects albedo, the fraction of solar energy reflected back to space, because oceans and vegetated land absorb more sunlight than ice and bare rock. In the mid-Cretaceous, with limited ice cover and extensive dark water surfaces, the planetary albedo is likely lower than today, further favouring a warm state. Within this framework, local anomalies and puzzles emerge. In some sedimentary basins, evidence suggests rapid meter-scale sea level fluctuations superimposed on the long-term high stand, occurring over timescales of hundreds of thousands of years or less. The causes of these relatively swift changes are not fully resolved. They may reflect regional tectonic adjustments, changes in dynamic topography driven by mantle flow beneath the continents, or variations in water storage on land in lakes and groundwater systems. Some researchers have explored whether limited ice sheets could still wax and wane in high altitude or polar mountain ranges, even in a generally ice-free world, contributing to shorter-term sea level variability. The evidence for significant ice during the peak of the long summer remains sparse and debated, but the very existence of these rapid fluctuations underscores that even in its drowned state, the Earth system retains degrees of freedom that allow coastlines to migrate on timescales relevant to evolution and ecosystem turnover. The fractured geography of the Cretaceous long summer thus plays a dual role. It is a consequence of high temperature and vigorous tectonics, and it is a driver of further climatic and ecological complexity. By creating a planet with extensive shallow seas, fragmented continents, and intricate coastlines, the high stand of sea level ensures that many species live in environments close to shifting boundaries. As the narrative of this interval continues, these boundaries become the sites where major transitions unfold, from reorganized marine food webs to the rise of new dominant predators and herbivores. The drowned coasts and interior seas form the stage on which the rest of the long summer's story plays out, and they frame the question of how close Earth has come in deep time to the limits of its own design. In the hot, flooded world of the long Cretaceous summer, the seas become both generous and hostile, supporting great abundance in some layers, while quietly undermining long-established forms of life. The changes that reshape the atmosphere and geography also reach deeply into the structure of marine ecosystems. Warm surface waters, high nutrient input in certain regions, and an altered circulation pattern produce conditions that at first appear favourable to many organisms. Plankton thrive in sunlit waters. Small fish and invertebrates feed on this constant supply of microscopic plants and animals. Yet beneath this surface activity, the interior of the oceans moves toward a more precarious state. The same warmth that enhances productivity in the upper ocean also strengthens stratification. Surface waters remain buoyant and do not mix as readily with deeper layers. Organic material produced near the top sinks and decays, consuming oxygen as it falls through the water column. If fresh oxygenated water does not renew the depths, large volumes of the ocean become oxygen poor. Sediment records from this time show that during the peak of the thermal maximum, this process intensifies enough to generate widespread low oxygen conditions, especially in mid-depth and deeper zones of many basins. The signature of these episodes appears as dark, fine-grained deposits enriched in organic matter and certain trace elements that accumulate when bottom waters lack sufficient oxygen. These oceanic anoxic events are not continuous. They come in pulses that last for hundreds of thousands of years, superimposed on the broader warm background. Each pulse marks a period when the balance between oxygen supply and demand tilts in favour of depletion, and each affects marine life in ways that depend on depth location and biological sensitivity. For many surface-dwelling organisms, conditions remain tolerable. Light nutrients continue to support plankton blooms and predators that hunt in the upper layers, including fish, and some reptiles can persist. For others, especially those that rely on well-oxygenated deeper waters or on particular coastal environments, the changes prove more serious. Among the groups most strongly impacted during this interval are the ichthyosaurs, marine reptiles, that had ruled large parts of the oceans since the early Mesozoic. These animals, with streamlined bodies and powerful tails, had adopted a lifestyle convergent in many respects with that of modern dolphins and some large fish, though they belong to a very different branch of the tree of life. For tens of millions of years they had diversified into a wide range of forms and sizes, occupying roles from small pursuit predators to giants that fed on large prey. By the time of the Cretaceous thermal maximum, however, their diversity is already in decline. The fossil record shows that the richest variety of ichthyosaurs occurs earlier, and that by the mid-Cretaceous only a few lineages remain. Around the interval of peak warmth and expanded anoxia, the last of these lineages disappears. The exact causes of their final extinction are still under study. Several mechanisms may have acted together. environmental changes associated with the long summer, such as shifts in prey, availability, water temperature structures, and oxygen levels may have narrowed their ecological options. Competition with emerging groups of predators, including some large fish and early forms of other marine reptiles, may have added further pressure. Reproductive strategies and life history traits that once favoured their success may have become disadvantageous in the new conditions. What is clear is that after a span of well over 100 million years, the ichthyosaurs vanish from the fossil record during this warm and unstable oceanic interval. A similar, though not identical, pattern affects another group of marine reptiles that had long been apex predators, the large short-necked forms often referred to as pliosaurs. These animals had massive heads, strong jaws, and bodies suited for powerful swimming, and for a long time they sat near the top of marine food webs, preying on other reptiles, large fish and cephalopods. Through the Jurassic and into the early Cretaceous, they were widespread and diverse. As the long summer advances, their record becomes patchier and their diversity declines. By the time the thermal maximum is fully developed, many of the classic large pliosaur lineages have either disappeared or are represented only by a few late forms, which also eventually fade. Here again, the reasons are likely complex. Warmer, more stratified seas, periodic low oxygen events, and changing prey communities all alter the conditions that originally supported these giant predators. New competitors emerge that can exploit different parts of the altered marine environment. Because these extinction patterns occur across wide geographic ranges and approximate the timing of major oceanic anoxic events, they raise questions about thresholds in the marine system. There may be combinations of temperature, oxygen distribution, and food web structure beyond which certain large specialized predators cannot easily adapt. Once crossed, these thresholds may lead not to gradual adjustment, but to relatively rapid loss on geological timescales, even as other groups continue or expand. Smaller organisms and those with flexible diets and life histories are often better able to track shifting habitats and resources. The disappearance of ichthyosaurs and large pliosaurs then does not indicate a general collapse of marine ecosystems. Instead, it signals a reconfiguration in which some long-dominant forms yield space to others better suited to the new conditions. The seas of the long summer become dangerous in a different way. For large air-breathing marine reptiles adapted to particular niches, the spreading of oxygen, pore zones constrains their range. For animals depending on certain prey species that decline, feeding becomes more difficult. For those tied to coastal or shelf environments that are repeatedly affected by local anoxia or rapid environmental change, habitats become unstable. These stresses favour traits such as ecological flexibility, rapid reproduction, and the ability to exploit new food sources while disfavouring highly specialised top predators whose success depends on stable multi-level food webs and wide access to well-oxygenated waters. To present day scientists examining this record, one of the intriguing aspects is the timing of these losses relative to the peaks of environmental stress. In some regions, the last occurrences of ichthyosaurs coincide closely with the most intense black shale deposition. In others, they precede or lag slightly behind. This variability suggests that while global processes set the overall context, local and regional factors such as basin geometry, circulation patterns, and the composition of local faunas modulate outcomes. There is no single line drawn across a map of the Cretaceous Ocean where one can say conditions suddenly become uninhabitable. Instead, there is a patchwork of crises and partial recoveries in which some basins fare worse than others, and some lineages survive longer in refuges before disappearing. The perceived emptiness of the seas, therefore, is not a literal absence of life. It refers to the loss of particular iconic forms that had shaped marine ecosystems for ages. In the spaces they leave behind, other organisms begin to expand. Some fish lineages attain larger sizes and more formidable roles as predators. Certain groups of reptiles that had previously occupied more marginal niches in nearshore or shallow environments begin to diversify and move into open marine settings. Among these are the mosasaurs, which will feature more strongly in the next stage of the story. Sharks and their relatives also show signs of increased diversity and body size. The long Cretaceous summer thus acts as both a filter and a generator. It filters out some lineages that cannot accommodate the combination of high-temperature altered oxygen regimes and geographic fragmentation. It generates opportunities for others that can use these same changes to expand. The disappearance of long-ruling marine reptile groups is one of the clearest and most dramatic outcomes of this filtering. Their extinction leaves a mark not only in the fossil record but also in the structure of subsequent marine ecosystems, which never again include the same combination of large dolphin-like reptiles and massive short-necked predators that once dominated the Jurassic seas. At the same time, this reshaping of marine life raises open questions about the sensitivity of complex food web structures to sustained climate forcing. The Cretaceous thermal maximum demonstrates that the Earth system can maintain very warm conditions for millions of years, while supporting high levels of biological productivity. Yet it also illustrates that under such conditions, particular ecological strategies may become less viable. Long-lived, highly specialized lineages that once used stability to build complex roles may find that stability replaced by a dynamic, patchy environment where flexibility is more advantageous. Whether similar patterns might emerge under other warm climate regimes, including those that could appear in different contexts, remains an area of active scientific interest. The long summer seas, with their combination of richness and selective loss, thus form a critical turning point in the history of marine life clearing space for new dynasties of predators that will come to define the later Cretaceous oceans. With the decline and disappearance of ichthyosaurs and the reduction of many large pliosaurs, the oceans of the long Cretaceous summer do not fall silent. Instead, they reorganize. New rulers step into the opening spaces, and some long-present lineages expand into roles they had not yet fully explored. Among the most prominent of these emerging powers are sharks and mosasaurs, whose histories intersect with the altered conditions of the thermal maximum in ways that illustrate how changing environments can redirect evolutionary trajectories. Sharks and their relatives have existed for hundreds of millions of years, by this point surviving earlier extinctions and climate shifts through a combination of durable body plans and flexible ecological strategies. In the earlier Mesozoic seas, however, they often share or cede the top predator roles to large marine reptiles. Many lineages specialize in mid-sized prey or occupy niche positions in complex food webs. During the Cretaceous long summer, this balance begins to change. Warmer, more stratified oceans and periodic anoxic events rearrange prey distributions and remove some of the largest reptilian competitors. At the same time, high surface productivity in many regions supports abundant fish and smaller reptiles, providing rich hunting grounds for agile, fast-moving predators. In this context, several groups of mackerel-like sharks increase in size and prominence. Fossil teeth and vertebrae from mid-Cretaceous sediments document the appearance of large forms such as Cardobiodon, a shark that grows to lengths comparable to a modern large great white. These animals possess robust bodies, strong tails and cutting teeth capable of slicing into sizable fleshy prey. Their remains are found in deposits from what are now North America, Europe, and parts of Asia and Australia, indicating wide distributions within the interior seaways and adjacent oceans. Their presence suggests that by the time of the thermal maximum, sharks are not only filling mid-level predatory niches, but are also occupying the apex positions vacated by some reptiles. Another member of this expanding predatory guild is Cretidus, known primarily from large teeth and associated skeletal fragments recovered in marine sediments. Estimates based on these remains indicate that some individuals reach lengths on the order of many tens of meters, placing them among the largest predatory sharks known from the Mesozoic. Their teeth are broad with cutting edges and complex root structures suited for gripping and processing substantial prey. Stomach contents preserved in rare specimens include fragments of marine turtles and possibly other large vertebrates, confirming that these sharks interact with some of the most heavily armoured animals of their time. Alongside these species such as Cretoxorhina, sometimes informally compared with modern lamnid sharks, appear as fast, powerful hunters in the mid to upper trophic levels of the western interior seaway and other basins. Their skeletal anatomy inferred from well-preserved fossils suggest high swimming performance and sustained pursuit of agile prey. Together, these sharks form a predatory framework that differs from earlier periods, dominated by enormous reptiles with paddle-like limbs and rigid trunks. The new shark assemblages are more fish-like in their movements capable of rapid acceleration and long-distance cruising across open water. Not all shark responses to the long summer involve larger size and increased ferocity. The altered ocean structure also supports unusual specialist forms. One of the more intriguing examples is Aquilolamna, a shark known from early Cretaceous rocks that appears to persist into parts of the warm interval and exemplifies a plankton-feeding lifestyle. Its fossils reveal elongated wing-like pectoral fins and a body shape reminiscent of later manta rays, though it belongs to a different branch of the shark family tree. Such morphology points towards slow, graceful swimming through upper waters, using broad fins to stabilize and maneuver, while filtering small organisms from the water. In the context of the long summer with high productivity and stratified layers, such filter feeders may find sustained opportunities. Their presence illustrates that not every evolutionary response to a stressed ocean is aggressive. Some lineages adapt by exploiting the oversupply of small organisms that thrive in warm, nutrient-rich surface waters. While sharks expand both upward and sideways in ecological space, another group of marine reptiles rises from nearshore obscurity to become emblematic predators of the late Cretaceous, the mosasaurs. These animals begin as relatively small lizard-like forms inhabiting coastal and shallow marine environments. Early representatives such as Dallasaurus display limb structures that still retain many features suited for life on land or in shallow water, including well-developed digits and limited modification into flippers. As time passes and the long summer progresses, successive lineages show increasing adaptation to fully marine life. Limbs elongate and flatten into paddles. Tails develop deep flukes supported by reinforced vertebrae improving propulsion. Bodies elongate and skulls become more robust with jaws and teeth specialized for gripping and tearing prey in open water. Fossils from the Turonian and subsequent stages document a rapid diversification of mosasaurs in multiple basins. Some genera, such as Tethosaurus and Halosaurus, occupy intermediate sizes and likely feed on fish, smaller reptiles and cephalopods in shelf and slope environments. Others grow larger, entering the apex predator role. Tylosaurus, a genus well represented in the western interior seaway, exemplifies this trend. Early species that appeared during or shortly after the peak of the thermal maximum reach lengths of several tens of meters and possess elongated snouts, powerful jaw muscles and interlocking teeth. Their anatomy indicates a capacity for swift ambush-based attacks and for tackling prey that includes other large vertebrates. Jaw and stomach contents from some specimens include bones of smaller mosasaurs, marine birds, and sizable fish, confirming their top position in the food web. The timing of mosasaur radiation overlaps with the decline of earlier reptilian apex predators and with the expansion of shallow and interior seas. This coincidence invites consideration of cause and effect. The flooded continental margins and interior basins of the long summer create extensive, warm, relatively protected marine habitats with abundant prey. These environments are well suited to reptiles that can exploit both nearshore and open water resources, and that can adjust to episodic low oxygen events by surfacing to breathe. Mosasaurs as air-breathing predators with flexible body plans derived from terrestrial ancestors fit this opportunity. As they evolve more efficient swimming adaptations and larger sizes, they become increasingly effective at dominating these basins. Their success may also be aided by the reduction of other marine reptile competitors, and by the availability of new prey types including the large sharks and turtles that flourish under the altered conditions. The coevolution of sharks, mosasaurs and other marine organisms during the long summer thus produces a distinctive pattern of antagonistic and opportunistic interactions. Sharks prey on smaller reptiles, fish and turtles. Mosasaurs prey on sharks, fish and other marine reptiles. Both groups respond to the same broad physical drivers, yet their evolutionary paths diverge in form and strategy. Sharks refine cartilaginous skeletons and efficient gill-based respiration to exploit a range of depths and swimming styles. Mosasaurs refine lung skeletal reinforcements and flippers for powerful strokes and breath-hold dives. In some environments, the two groups likely compete directly for similar prey. In others, their roles are staggered by depth or habitat. Observers reconstructing these dynamics must rely on scattered fossils and comparative anatomy. So many details remain unresolved. Which group dominates in a given basin at a given time may depend on local circulation patterns, productivity and historical contingencies such as which lineage arrives first or diversifies most rapidly. One of the striking aspects of this turnover is that it produces a marine ecosystem whose top predators are for the first time in many tens of millions of years, largely creatures that either evolved on land or come from ancient fish lineages that never fully ceded their roles. The long summer seas, once emblematic for their giant, long-established marine reptiles, with deep evolutionary roots in older oceans, now feature lineages whose major radiations are linked more closely in time to the warm interval itself. Sharks seize the chance to grow larger and more diverse when conditions favour their physiology and reproductive strategies. Mosasaurs take advantage of geography and prey structure to invade and then dominate environments that earlier reptiles had held. The idea that climate and tectonics can act as selective filters and drivers at the level of entire functional groups becomes more concrete when viewed through this lens. Warming and stratification do not simply stress marine life in general. They alter the relative performance of different body plans, metabolic systems, and life histories. In the mid-Cretaceous, those alterations channel energy and opportunity toward sharks and mosasaurs. The rise of these predators also feeds back into the structure of food webs. Their hunting pressure shapes the behavior, distribution, and evolution of prey species. Schools of fish may adopt different migration patterns or spawning grounds in response to predation risk. The size distributions of turtles, cephalopods, and smaller reptiles may shift as individuals that can outgrow vulnerability gain advantages. Over time, these interactions sculpt a marine biosphere that is distinct from that of earlier periods, even if many lower-level components such as plankton and invertebrates remain superficially similar. From the perspective of the long narrative of life, the reign of sharks and mosasaurs in the Cretaceous long summer is temporary ending with the broader biotic turnover at the close of the era. Yet within its own frame it represents a stable self, reinforcing configuration that persists for millions of years under sustained warm conditions. The fact that this configuration arises from the same environmental forces that extinguish earlier marine reptile dynasties underscores how sensitive apex communities can be to relatively slow, large-scale physical changes. The oceans of the long summer are thus not merely hotter versions of earlier seas. They are structurally different, and the new predators that crown their food webs are enduring markers of that difference. On land, the long Cretaceous summer expresses itself through forests, open woodlands, and savanna-like landscapes that stretch across continents, providing the stage on which some of the largest animals in Earth's history evolve and move. Elevated carbon dioxide and warm temperatures favour vigorous plant growth in many regions. Conifers, cycads, ferns, and an increasingly diverse array of flowering plants share space in complex mosaics. In low latitudes and along flooded coastal plains, broad river systems weave through humid forests and wetlands. At mid-latitude, seasonal climates support mixtures of forest and more open environments where patches of trees alternate with expanses of low vegetation. At high latitudes near the poles that are today frozen mild conditions and long summer daylight allow forests to reach right into zones that sometimes experience months of continuous light, followed by months of darkness. In this terrestrial world, the long summer accelerates some evolutionary trends and redirects others. One of the most conspicuous responses involves sauropods, the long-necked, large-bodied herbivorous dinosaurs that had already been present for many tens of millions of years. Before the Cretaceous thermal maximum, sauropods have achieved large sizes in multiple lineages, with some species in the Jurassic and early Cretaceous reaching lengths of several tens of meters and masses comparable to several modern elephants. During the warmest part of the late Cretaceous, especially in the southern continents, this pattern continues and intensifies. Fossil evidence from South America indicates that titanosaurs, a group of sauropods adapted to a range of environments, diversify and produce some of the largest known terrestrial animals. Among them, Argentinosaurus stands out as a benchmark for extreme body size. Based on partial skeletons that include vertebrae and limb bones, paleontologists estimate that adult individuals may reach lengths on the order of more than 30 meters and masses around several tens of tons, with some reconstruction suggesting values near 80 tons. Even at the lower end of these ranges, such animals dwarf most other land vertebrates. Their necks, torsos, and tails contain a complex network of air-filled spaces within the bones, which reduce weight while maintaining strength, and their limbs form thick columns capable of supporting great loads. The environments that support such animals during the long summer combine abundant plant biomass with relatively mild seasonal extremes. In parts of what is now Patagonia, for example, geological formations from this time preserve evidence of broad floodplains crossed by rivers, bordered by forests and more open vegetation. Soils suggest periodic flooding and drying, indicating that while the climate is warm, it is not uniformly wet. Plants must tolerate both standing water during high river stages and drier conditions between floods. Sauropods navigating these landscapes can exploit a wide vertical range of feeding heights, browsing from low shrubs up to tree canopies. Elevated carbon dioxide may enhance the productivity of some plant groups, though it can also alter leaf chemistry, affecting nutrient content and defensive compounds. The net effect on herbivores is not straightforward, but the sheer volume of vegetation in these warm, extensive habitats appears sufficient to sustain herds of large dinosaurs. The physiology that permits sauropods to attain such sizes under these conditions remains an area of active study. Their long necks allow them to reach large feeding areas without moving their massive bodies as frequently, potentially reducing energy costs. Their lung and air sac systems, inferred from skeletal anatomy, resemble in some respects those of modern birds, enabling efficient gas exchange and perhaps better heat management in warm climates. Their growth patterns, deduced from bone histology, indicate relatively rapid growth to large sizes, which may provide advantages in escaping predation and in exploiting resource-rich environments. In the context of the long Cretaceous summer, these traits may interact with climate in ways that favour gigantism for certain lineages. Warm temperatures can reduce the energetic cost of maintaining body temperature for large ectothermic or mesothermic animals, while high plant productivity can support their feeding demands. At the same time, the thermal environment cannot be unlimitedly favourable. Very large bodies must dissipate metabolic heat, and in a hot world this becomes more challenging. The geographic distribution of the largest sauropods, with many found in regions that, while warm, may not be at the absolute equatorial peak of temperature, could reflect an interplay between resource availability and thermal constraints. Fire also plays a role in these ecosystems. In a warm, oxygen-rich atmosphere with extensive vegetation, lightning and other ignition sources can produce frequent wildfires, particularly in seasonally dry regions. Charcoal fragments in Cretaceous sediments demonstrate that fires occur across a range of environments. Their frequency and intensity vary with climate and vegetation type, but they are common enough to shape plant communities. Fire can clear forests, promote the spread of fire-adapted species, and maintain open habitats in which grasses and low shrubs can thrive. These open areas, in turn, may favour large herbivores that move in groups and feed over wide areas. The balance between closed forest and more open vegetation under long summer conditions is therefore not fixed, but influenced by the interaction of climate fire and herbivory. Large sauropods and other herbivorous dinosaurs act as ecosystem engineers, trampling, browsing and transporting nutrients through their movement and waste. Their presence may reinforce certain vegetation structures, just as herds of large mammals do in some modern savanna systems. In regions where sauropods are particularly abundant, their feeding can limit tree regeneration and encourage more open canopies, which in turn influence local microclimates. The long Cretaceous summer thus produces landscapes where climate and animals co-shape the environment. Not all parts of the world show the same response. In the northern hemisphere, sauropod diversity decreases in some regions compared with earlier times, while ornithischian herbivores, including hadrosaurs and ceratopsians, become more prominent. In the southern continents, particularly in South America, sauropod diversity and size increase. This asymmetry may relate to differences in continental position, climate zones and historical biogeography. The high sea level of the long summer isolates land masses to varying degrees, reducing faunal interchange and allowing different evolutionary experiments to proceed in parallel. In southern latitudes, titanosaurs explore the upper bounds of size in environments that favour their feeding strategies. In northern regions, other herbivore clades, some of which possess advanced chewing mechanisms, and complex tooth batteries exploit different plant communities under slightly different climatic regimes. The exact combination of factors that enables titanosaurs such as Argentinosaurus to reach extreme sizes at this particular time remains uncertain. Hypotheses include high plant productivity, reduced predation risk for adults in fragmented landscapes, favourable climate for growth and thermoregulation, and intrinsic evolutionary innovations in body plan and physiology. Constraints may also limit the number of lineages that can follow this path. The skeleton of a giant sauropod must solve mechanical and circulatory challenges that few designs can meet. Even within titanosaurs, only a subset appear to have approached the largest sizes, suggesting that gigantism is the outcome of specific evolutionary trajectories rather than a general tendency under warm conditions. The long summer also shapes plant evolution. Flowering plants, which first appear earlier in the Cretaceous, diversify strongly during this interval. Their leaves' reproductive structures and growth forms vary widely from small shrubs to large trees. In some ecosystems, they begin to displace or integrate with older gymnosperm-dominated forests. Their interactions with herbivores, pollinators, and seed dispersers initiate new ecological relationships. The high carbon dioxide climate may provide conditions in which some flowering plants can rapidly exploit disturbed areas created by fire floods or dinosaur activity spreading across landscapes that are repeatedly reset. Over time, these dynamics contribute to the eventual dominance of flowering plants in many terrestrial ecosystems, a trend that will continue into later periods. The interplay between forests and climate under long summer conditions also influences regional hydrology. Deep-rooted trees and dense understory vegetation can enhance evapotranspiration, returning moisture to the atmosphere and sustaining local rainfall. In some regions, this feedback helps maintain humid conditions even far from the coasts, while in others, where vegetation is more sparse or frequently disturbed, soils may dry more between rainfall events. The distribution of forests, open woodlands and savannas under conditions of high carbon dioxide and warmth is thus an emergent property of multiple interacting processes, including climate, fire, animal activity and plant evolution. From a distance, it is tempting to think of the Cretaceous long summer as uniformly lush. The reality is more varied. Some areas are densely forested and humid, others are open and seasonally dry. Some support giant sauropods in substantial numbers, others are dominated by smaller herbivores with different feeding styles. Across all these environments, however, the baseline of temperature and atmospheric composition sets a consistent frame. Winters are generally mild storms, and droughts occur within a warmer range, and growing seasons are extended. Within this frame, life explores modes of existence that are not possible in colder, more strongly seasonal worlds. The land of giants, with its titanosaurs and extensive forests, is one visible manifestation of this exploration. The fact that it emerges during a period when the planet approaches some of its long-term thermal and sea level limits adds an element of contingency to its existence. If tectonic and volcanic conditions had been different, or if feedbacks had curtailed warming earlier, such extremes of body size and landscape configuration might not have occurred. In that sense, the giant sauropods and their habitats can be seen as temporary solutions that the Earth system permits, while it passes through a particular combination of conditions. As the narrative continues, the same long summer that enables their flourishing will also shape the evolution of the predators and other herbivores that share their world, and the questions of how stable such a configuration can be, and how it ultimately ends remain open within the deeper story of the Cretaceous. As the long Cretaceous summer reshapes forests, floodplains, and open woodlands, it also forges hunters and other unusual dinosaurs whose bodies and behaviours make sense only against a backdrop of persistent warmth and abundant plant growth. On the same southern continents where titanosaurs reach their greatest sizes, large theropods diversify and refine strategies for tackling massive prey, while in other regions peculiar clawed herbivores and towering feathered forms explore very different ways to coexist with the heat. Together, these animals illustrate how the climate of the thermal maximum drives not just who survives, but how life experiments with form and function. In South America, particularly in what will later be known as Patagonia, several lineages of large carnivorous theropods evolved during and after the peak of the long summer. Among them are Carcharodontosaurids, a group characterized by deep skulls, long jaws and teeth with fine serrations reminiscent of the cutting edges of a well-honed blade. Genera such as Maposaurus and Giganotosaurus present in earlier stages set the stage with large body sizes and powerful builds. During the warmest intervals, additional forms such as Meraxes and other related species occupy similar ecological space. These animals reach lengths exceeding 10 meters and masses of several tons, placing them among the largest terrestrial predators known. Their anatomy suggests that they are adapted to a lifestyle involving active pursuit or ambush of large herbivores, including titanosaurs. Their necks and forelimbs, though not as elongate as those of some other theropods, are muscular and capable of controlling struggling prey, while their jaws deliver deep slicing bites. Evidence from bone beds preserving multiple individuals of some species hints that at least occasionally they may have occupied the same space and perhaps interacted socially or at carcasses, though the extent of coordinated group hunting remains uncertain. The presence of several large theropod species in the same region at overlapping times raises questions about how they partition resources in a landscape dominated by giant sauropods. Differences in skull shape, tooth morphology, and limb proportions suggest subtle distinctions in prey preference and hunting strategy. Some may specialize in targeting younger or smaller sauropods, others may focus on medium-sized herbivores or on scavenging. The warm climate and high plant productivity mean that herds of large herbivores can be relatively dense, providing a broad resource base. At the same time, the heat imposes physiological constraints on both predators and prey. Activity patterns may shift toward cooler parts of the day, and shade and water sources become important elements of habitat use. The long summer thus frames these predator-prey dynamics within a narrower range of temperature variation, but a high overall energy throughput favoring large active carnivores that can exploit abundant biomass without facing prolonged cold seasons. South America is not the only region where hunters forged in heat develop distinctive traits. In other parts of Gondwana and in Laurasian continents further north, abelisaurids occupy prominent roles among large theropods. These dinosaurs have relatively short, deep skulls, often with ornamentation such as ridges or horn-like structures, and extremely reduced forelimbs. Their hind limbs are well developed, indicating strong running ability. In Patagonia, forms such as Carnotaurus and Scorpiovenata represent this clade-sharing environments with Carcharodontosaurids and Titanosaurs. Their teeth and jaw mechanics suggest a powerful bite adapted for inflicting puncture and tearing damage, and their body plans hint at ambush tactics in varied terrain. The coexistence of Carcharodontosaurids, abelisaurids, and other theropods such as Megaraptorans in the same broad regions illustrates how the long summer's fragmented geography and rich ecosystems can support multiple apex and near-apex predators simultaneously. Megaraptorans with elongated forelimbs and large curved claws on their hands represent another branch of the theropod experiment under warm conditions. Their anatomy indicates a combination of speed and grasping ability. In some reconstructions, they are envisioned as agile hunters that may use their claws to seize and stabilize prey before delivering bites, perhaps using wooded cover or broken terrain to their advantage. The long Cretaceous summer's extensive forests and complex riverine networks provide many such environments where an agile predator could exploit both open and closed habitats. Moving northward to Asia and parts of what will become North America, the character of the theropod response shifts. Here the thermal maximum coincides with the diversification of several groups that are not primarily top predators, but rather fill intermediate or specialized roles in the food web. Among these are therizinosaurs, a group of theropods that, despite their ancestry among carnivorous lineages, adopt largely herbivorous or mixed diets. Their skeletons reveal long necks, large torsos and forelimbs, equipped with extremely elongated claws, in some cases exceeding 1/2 meter in length. Their skulls are small relative to body size, with teeth and beaks suited to processing plant material rather than tearing flesh. In warm, seasonally variable environments with dense vegetation, these animals likely use their claws to pull down branches, strip foliage, or defend themselves from predators. Their bodies sometimes covered in filamentous integument, and their large gut capacity suggest a strategy of processing fibrous plants in regions where forests and shrubs are plentiful. The long summer's climate, by supporting extensive vegetation and long growing seasons, provides ecological room for such unusual herbivores to evolve and persist. Alongside them, oviraptorosaurs explore another path. Some, like Gigantoraptor from Mongolia, reach sizes comparable to large theropods with estimates of body mass in the range of several tons and heights at the hip comparable to modern giraffes. Their anatomy, with toothless beaks, robust legs, and evidence of feathers, suggests omnivorous diets and active lifestyles. In floodplain and forest edge environments under warm conditions, such animals may feed on a mixture of plant material, small vertebrates, eggs, and invertebrates. Their large size and likely social behaviours inferred from nesting evidence in smaller relatives could influence local ecology through trampling seed dispersal and predation on smaller animals. The climate of the long summer may facilitate their expansion by reducing thermal stress in high latitudes and by maintaining productive plant communities that can support large generalist omnivores. Even among more traditionally carnivorous theropods, the thermal maximum sees the continued presence and diversification of tyrannosauroids, though the largest iconic forms appear later after the absolute peak of the long summer. In the mid-Cretaceous, tyrannosauroids are mostly mid-sized predators, with proportionally longer arms and more slender builds than their later relatives. They occupy roles that may involve preying on smaller herbivores, scavenging, and competing with other mid-level predators. Their eventual ascent to apex predator status in some regions coincides with changes in fauna and possibly climate trends as the long summer gradually eases, but their roots lie in this earlier warm interval. The persistence and spread of these lineages in a hot world demonstrate that not all evolutionary trajectories are tightly tied to a single climate state. Some groups can bridge transitional regimes. The influence of heat on dinosaur biology extends beyond body size and diet. Growth rates, metabolic strategies, and reproductive patterns all interact with climate. Bone histology studies suggest that many theropods and large herbivores grow rapidly to near adult size, an advantage in environments with high predation pressure and stable growing seasons. Warm temperatures and long daylight at high latitudes may allow for near-continuous or seasonally extended growth periods, while mild winters reduce the risk of juvenile mortality due to cold. Nesting and incubation in such a climate may also differ from those in cooler worlds. Eggs buried in warm soils or covered with vegetation in humid greenhouse conditions might benefit from stable thermal regimes, reducing the need for parents to regulate temperature as precisely as some birds do today. At the same time, intense rainfall events and periodic droughts could challenge nesting sites, requiring behavioral adaptations in nest placement and clutch timing. The long summer thus sets a stage in which high growth rates and flexible reproductive strategies are rewarded, and where the line between strictly warm adapted physiologies and more intermediate metabolic modes becomes blurred. One recurring feature in this array of hunters and specialists is the prevalence of feathers and filamentous body coverings in many clades, especially in smaller and mid-sized theropods. Insulating coverings may seem paradoxical in a warm world, but they can serve multiple functions, including display brooding and fine-scale temperature regulation. In environments where night's highlands or seasonal variations still bring cooler periods, insulation helps maintain stable internal temperatures, while in hot conditions, behavioral strategies such as seeking shade and adjusting activity patterns mitigate overheating. Feathers and similar structures become tools for controlling energy exchange with the environment, rather than simple responses to cold. The long Cretaceous summer provides a backdrop in which such multifunctional traits can be elaborated, decoupling them from a narrow association with cold climates. From a broader perspective, the diversity of theropods and other dinosaurs during the thermal maximum illustrates that a hot climate does not merely compress ecological possibilities, it rearranges them. Large hypercarnivores coexist with omnivorous giants, specialized herbivores drawn from carnivorous ancestry and mid-sized predators adapted to a range of microhabitats. The constant high baseline of warmth, combined with fragmented geography and varying moisture regimes, produces many separate arenas in which evolution can experiment. Some of these experiments, like the titanosaurs and giant carcharodontosaurids, push to extremes of size and specialization that may be viable only in such a world. Others, like feathered mid-sized predators and omnivorous forms, develop traits that will persist into later cooler climates. The hunters forged in the heat of the long summer, and the odd herbivores that share their landscapes thus form both an endpoint and a bridge in dinosaur evolution. Their existence speaks to the capacity of life to fill niches created by unusual climate states, and their eventual disappearance or transformation will be part of the larger question of how stable such states are. As the narrative shifts toward the polar realms, and then to the view from the distant future, these animals remain as reminders that the Cretaceous thermal maximum is not only a story of physics and chemistry, but also a story of how living systems take those conditions and turn them into bodies, behaviors, and communities that for a span of time make complete sense within their world. In the high latitudes of the long Cretaceous summer, the contrast between what is expected from modern experience and what the evidence reveals becomes sharper than almost anywhere else on the planet. Today, polar regions are defined by ice tundra and long periods of intense cold, with only short bursts of productivity in brief summers. In the mid-Cretaceous, under the influence of elevated carbon dioxide and rearranged oceans, those same regions host forests, rivers, and diverse communities of dinosaurs and other animals that endure months of light and months of darkness, in climates that remain on average surprisingly mild. Fossil sites in what are now polar or near polar zones of the Northern Hemisphere, including parts of Alaska and the Canadian Arctic, preserve bones, teeth, and trackways of hadrosaurs, ceratopsians, ankylosaurs, and small to mid-sized theropods. Similar evidence from southern high latitudes in what will become Antarctica and southern Australia shows that the polar story is not confined to one hemisphere. These remains are not isolated curiosities transported from distant regions. They are part of faunas adapted to local conditions. Growth rings in bones indicate that many of these animals spend year after year in high latitude environments, experiencing the full cycle of long summers and extended periods of low light or darkness. The climate that supports them is shaped by the same greenhouse conditions that warm the rest of the planet, but the effects are magnified near the poles. Elevated carbon dioxide and warm oceans reduce the equator to pole temperature gradient, allowing high latitude land areas to maintain average temperatures well above freezing, even during the coldest seasons. Sedimentary records and plant fossils from these regions suggest the presence of temperate forests with conifers, deciduous trees, and understory vegetation, similar in some respects to modern cool temperate woodlands. Tree rings and leaf features imply that while winters are cooler and darker than summers, they are not dominated by harsh frosts. Snow, if present, is likely seasonal and limited. This sets up a paradox. Light levels at high latitudes still vary strongly over the course of a year because Earth's axial tilt remains comparable to modern values. In summer, the sun stays above the horizon for long stretches, providing continuous or near-continuous daylight. In winter, it dips below the horizon for extended periods, leaving landscapes in twilight or darkness. Under present climatic conditions, such darkness contributes to deep cold. In the Cretaceous long summer, the same darkness occurs, but the temperature response is muted. Oceans that surround polar landmasses act as heat reservoirs, releasing energy accumulated during long summers back to the atmosphere. A thick greenhouse atmosphere slows the loss of infrared radiation to space. Clouds and moisture trap additional heat. As a result, winter nights are long but not severely cold. For the animals and plants of these regions, the challenge is less about surviving extreme low temperatures and more about coping with the absence of light and the seasonal decline in primary productivity. Plants adapt by entering periods of reduced growth during the dark months, storing energy, and resuming photosynthesis when the sun returns. Many trees appear to be deciduous shedding leaves before the onset of winter darkness. This behavior conserves resources and reduces damage from freezing events, however mild. Forests thin as winter progresses, opening understory spaces where litter seeds and stored plant material accumulate. Herbivorous dinosaurs using these habitats must find food in landscapes that become seasonally depleted. Evidence from bone growth patterns suggests that some high-latitude dinosaurs, such as hadrosaurs, may respond with seasonal growth modulation. During bright, warm summers, growth lines in their bones indicate rapid expansion, while in darker months growth slows. This pattern resembles that seen in some modern animals living in strongly seasonal environments, where physiological processes adjust to changing resource availability. Whether these dinosaurs migrate long distances to escape the darkest periods or remain year-round in polar regions has been a subject of debate. Trackways and bone beds dominated by juvenile and adult individuals of various sizes, as well as the sedimentary context of some sites, point toward at least partial year-round residency for some species. Long-distance migration through flooded, fragmented continents under Cretaceous conditions would require routes that are not always available, and young animals might find such journeys especially challenging. The idea that many polar dinosaurs stay in place and adjust their metabolism and behavior to cope with extended darkness fits with bone evidence and with the general capacity of vertebrates to adapt to seasonal cycles, though some lineages may still undertake regional movements. Carnivorous theropods in these environments face their own set of constraints. They must track prey that is less active or less abundant during winter. Their bones also show growth rings that may reflect seasonal changes in food intake. In a warm greenhouse world, thermoregulation at high latitudes may be less energetically costly, but the need to find sufficient food during the dark months still imposes limits. This combination of mild temperatures and low light availability makes polar Cretaceous ecosystems an unusual test case for dinosaur physiology. If some dinosaurs possess elevated metabolic rates and insulation, either from feathers or other structures, they may function well in cool, dark conditions as long as they can access food. If they rely more heavily on external heat, they benefit from the greenhouse climate that reduces cold stress, but still must manage activity patterns during extended nights. The fossil record does not provide direct measurements of metabolic rate, but bone microstructure, body proportions, and the presence of insulating coverings in related lineages support the idea that many dinosaurs operate at intermediate to high metabolic levels. The polar context strengthens this inference by showing that such physiologies can sustain active vertebrates through long periods without direct solar heating. The distribution and composition of polar forests add further mystery. Some plant fossil assemblages indicate surprisingly high diversity at high latitudes, suggesting that mild climates and long summers permit a variety of species to coexist. Others show dominance by a few tree types adapted to seasonal darkness. The arrangement of these forests affects albedo and energy exchange feeding back into regional climate. Dense dark canopies absorb more sunlight during long summer days, warming the surface and contributing to the maintenance of mild temperatures. In winter, the absence or reduction of leaves may increase reflection of whatever light is available, but also expose soil and understory layers that can store and release heat. The interplay between vegetation and climate at these latitudes remains an active area of research, with models exploring how different forest configurations influence energy budgets. Observations from modern high-latitude forests offer some guidance, but the Cretaceous long summer presents combinations of temperature, day length, and atmospheric composition that have no direct analogue today. Another layer of complexity arises from the potential influence of cloud cover and storm tracks in polar regions under warm conditions. Climate simulations suggest that high latitude zones in a greenhouse world may experience frequent cloudiness and precipitation, especially during transition seasons. Clouds can moderate surface temperatures by reflecting solar radiation and trapping infrared emissions. Their net effect depends on altitude thickness and timing. In the Cretaceous long summer, they may help smooth out temperature variations between seasons and between day and night, further stabilizing conditions for plants and animals while altering the light environment in subtle ways. Extended twilight under thick clouds could prolong low light periods and affect photosynthesis schedules and behavior. The polar realms of this era thus combine structural familiarity in the form of forests and rivers with unusual temporal patterns. Days and nights stretch to lengths absent at lower latitudes, and seasons are defined more by light and plant phenology than by temperature extremes. The animals and plants that inhabit these regions appear to exploit this framework rather than being constrained solely by cold. Dinosaurs browse and migrate through forests that spend months in shade, and small mammals and other vertebrates occupy niches in leaf litter and burrows that buffer environmental changes. From the perspective of the broader Cretaceous system, these polar ecosystems are both integral and distinctive. They receive heat transported from lower latitudes and return some of it via atmospheric and oceanic circulation. They participate in global carbon cycling through plant growth and soil processes. At the same time, they host evolutionary experiments that may not occur elsewhere. Patterns of dwarfism or gigantism, altered life histories, and unique behaviours could emerge in response to the intersection of mild temperatures and extreme photoperiods. Some high-latitude dinosaur species may evolve smaller body sizes to cope with winter resource limitations, while others maintain larger sizes that allow them to store energy and reduce relative heat loss. The rock record captures only a fraction of this variation, leaving many questions open. Comparisons between polar and non-polar dinosaur communities show both shared lineages and distinct species pointing to a mixture of dispersal and local adaptation. The fact that faunal differences are sometimes sharper than expected based purely on geography suggests that the polar light regime exerts its own selective influence over and above temperature and plant composition. The northern realms and southern polar zones of the long Cretaceous summer therefore stand as test cases for how life can adjust to climates that are warm yet governed by unusual cycles. They demonstrate that a hot Earth does not necessarily erase seasonal structure, it changes its dominant axes. Light and darkness become more important than temperature magnitude in dictating annual rhythms. Mild winters do not remove the need for adaptation to scarcity when plants reduce activity. The existence of thriving dinosaur communities at such latitudes during the thermal maximum challenges simple categorizations of the Cretaceous as uniformly tropical and points toward a more nuanced picture of a world in which nearly all regions are relatively warm, yet each retains its own pattern of constraints. As the narrative turns toward the present day, these polar ecosystems offer more than historical curiosity. They provide examples of how a greenhouse Earth can maintain habitable, even rich conditions at high latitudes while still imposing distinctive seasonal stresses. The details of how dinosaurs and plants respond to this combination remain only partially understood, leaving open questions about behaviour physiology and community structure that continue to motivate fieldwork and modelling. The high-latitude forests and their inhabitants caught between continuous summer light and prolonged winter darkness embody the peculiar balance of the long Cretaceous summer, a balance in which warmth is extended but never entirely uniform, and in which even the poles participate in a climatic experiment near the upper bounds of Earth's usual range. In the present, the long Cretaceous summer exists only as a pattern in rocks, fossils, and subtle geochemical signals that scientists extract from scattered outcrops and cores. No instrument has ever measured its temperatures directly, no satellite has imaged its drowned coasts. Yet over the past decades, researchers from many fields have assembled a coherent picture of this interval that is precise enough to identify its broad structure and uncertain enough to leave important questions open. The story begins with field work. Sedimentary layers exposed in cliffs, road cuts, and drill cores show sequences of sandstone shale, limestone, and volcanic ash that were once rivers, seas, lagoons, and ocean floors. Within these layers lie fossils of dinosaurs, marine reptiles, fish plankton and plants, as well as microscopic shells and organic particles. By tracing these deposits across continents and correlating them using fossil assemblages and radiometric dates from volcanic minerals, geologists reconstruct the approximate timing of events. The Cretaceous thermal maximum emerges as an interval in the late Cenomanian and Turonian stages, when many indicators of warmth and sea level reach peaks. To turn this stratigraphic framework into a climate history, researchers turn to proxies measurements that stand in for temperature, carbon dioxide, and other variables. Oxygen isotope ratios in the calcium carbonate shells of marine microfossils provide one of the main tools. Because the ratio of heavy to light oxygen in these shells depends on the temperature and composition of the water in which the organisms grew, careful analysis can reveal past sea surface and deep ocean temperatures. In cores that span the mid-Cretaceous, these ratios shift in ways consistent with significantly warmer conditions than today, especially in high and mid-latitude regions. Other proxies, such as the composition of organic molecules produced by certain plankton, support similar conclusions, though they come with their own uncertainties. To estimate atmospheric carbon dioxide, scientists examine the stomatal density of fossil leaves, the boron isotopic composition of marine carbonates, and the carbon isotopic fractionation in organic matter. Each method relies on a known relationship between carbon dioxide levels and the process being measured, such as how plants regulate gas exchange through tiny pores, or how seawater chemistry responds to dissolved carbon. Combined, these methods suggest that during the long Cretaceous summer, carbon dioxide concentrations rise to several times pre-industrial values, likely reaching or exceeding a few thousand parts per million. The fact that different techniques converge on a high range increases confidence in this picture, even though precise values remain debated. Black shales and other organic rich sediments deposited in many basins during late Cenomanian and Turonian anoxic events add further pieces to the puzzle. Their wide geographic distribution, distinctive chemistry, and association with particular fossil assemblages indicate episodes when large parts of the ocean interior become oxygen poor. By correlating these layers with temperature and carbon records, scientists see that the strongest anoxic intervals coincide with the warmest phases of the long summer. This coincidence suggests that the combination of high carbon dioxide, warm stratified oceans, and altered circulation patterns pushes the system into a state where oxygen depletion becomes widespread. The exact thresholds and feedbacks involved, however, are still being refined. Numerical climate models provide a means to test whether the physics of radiation convection and fluid movement can reproduce the inferred Cretaceous climate given the reconstructed geography and estimated greenhouse gas levels. These models, originally developed to study modern and future climates, are adapted by changing continental positions, topography, ocean basin shapes, and atmospheric composition. When run under mid-Cretaceous conditions with elevated carbon dioxide, many models produce global temperature patterns that resemble the proxy data-reduced equator to pole gradients, warm high-latitude seas, and mild forested polar continents. Some also generate regions of stratified low oxygen, ocean interiors, and strong precipitation belts over flooded continental margins. Discrepancies remain. For example, some models struggle to attain the full warmth implied by certain high latitude temperature proxies without using very high carbon dioxide levels or additional feedbacks. This tension leads researchers to re-examine both the models and the proxy interpretations, and to explore whether factors such as cloud properties, aerosol distributions, or vegetation feedbacks operated differently under Cretaceous conditions. In this way, the long summer serves as a benchmark for understanding the climate system's sensitivity to greenhouse forcing. The comparison between the Cretaceous thermal maximum and modern warming arises naturally once these reconstructions are in place. there are clear differences in context. The long summer unfolds over millions of years, driven by tectonic and volcanic processes that gradually alter atmospheric composition. Modern anthropogenic warming proceeds over centuries, driven by rapid fossil fuel combustion and land use changes. The peak Cretaceous carbon dioxide levels reach values higher than those measured so far in the present, and sea levels stand far above current ones. Yet both cases involve the same basic physics of greenhouse gases, radiation, and feedbacks. For this reason, scientists sometimes look to the Cretaceous not as a direct forecast, but as a distant reference that shows what the Earth system can sustain when greenhouse forcing remains high for prolonged periods. This reference raises several lines of inquiry. One concerns the long-term evolution of climate under sustained high carbon dioxide. The Cretaceous demonstrates that Earth's feedbacks such as silicate weathering and organic carbon burial can eventually balance strong volcanic input at a warm equilibrium. Understanding how quickly these feedbacks operate and how they depend on geography and biology remains an open question. The burial of black shales during anoxic events, for example, removes carbon from the active cycle, but the rate at which this happens varies among basins and may depend on nutrient delivery and ocean circulation. Modern observations of oxygen minimum zones and coastal hypoxia provide analogues at small scales, but scaling these up to Cretaceous conditions involves uncertainties. Another line of inquiry concerns thresholds in marine ecosystems. The extinctions of ichthyosaurs and reductions in large pliosaurs during the long summer suggest that prolonged warmth and anoxia can restructure apex communities without causing mass extinction of marine life as a whole. This outcome contrasts with some earlier and later crises where rapid environmental changes lead to broader losses. Researchers ask what combinations of warming rate, anoxia extent, and other stressors delineate these different responses. The Cretaceous thermal maximum offers data on a relatively slow high stand state that supports high productivity yet eliminates some large specialists. In contrast, modern warming involves faster changes and additional stresses such as acidification and human exploitation. Comparing these situations helps clarify which aspects of Cretaceous behavior are general and which are specific to its setting. On land, the existence of giant sauropods, extensive forests at high latitudes, and diverse dinosaur faunas during the long summer raises questions about the relationship between climate and body size, vegetation patterns, and evolutionary innovation. The fact that some of the largest terrestrial animals ever known evolve and thrive under these conditions suggests that warm, high carbon dioxide climates can support extreme body sizes and rich ecosystems. At the same time, the eventual disappearance of these lineages even before the end of the Cretaceous hints that such configurations are not permanent. Changes in sea level, regional climates and vegetation, as well as shifts in faunal composition, all contribute to later turnovers. Disentangling which factors are decisive remains challenging. The fossil record is incomplete, and many sequences are interrupted by erosion or non-deposition. This incompleteness is itself a source of intrigue, prompting targeted searches in regions where key intervals may be preserved. The polar forests and dinosaur communities of the long summer receive particular attention in this context. They represent examples of ecosystems functioning under long daylight and darkness cycles in warm conditions, something not directly accessible today. Studies of their plant assemblages, soil structures, and animal remains aim to infer how energy and nutrients flow through such systems. The results feed back into general theories of how biodiversity, productivity, and environmental variability interrelate. They also inform thinking about how future high-latitude ecosystems might function if modern warming continues to reduce temperature contrasts and alter seasonality. Beyond Earth, the long Cretaceous summer sometimes appears in discussions of planetary habitability. A planet with high greenhouse gas levels and ocean-dominated surfaces might experience climates analogous to parts of the Cretaceous, with warm poles and reduced ice. Understanding how such a state behaves over long times, how stable it is, and how it interacts with biological processes, provides context for interpreting observations of exoplanets and for constraining models of early and future Earth. Here again, the Cretaceous record does not supply direct answers, but frames the space of possibilities with a real example. Perhaps one of the most enduring aspects of the Cretaceous thermal maximum from a scientific perspective is its dual nature. On one hand, it is a well-documented warm interval, with clear signatures in multiple proxies, consistent patterns across continents, and a coherent physical explanation rooted in plate tectonics and greenhouse gas physics. On the other hand, it retains unresolved puzzles, the precise carbon dioxide concentrations at different times, the details of ocean circulation under extreme warmth, the exact mechanisms that trigger and end anoxic events, and the reasons why some lineages flourish, while others decline. Each new core fossil site or model adds detail, but also reveals new complexities such as regional differences in temperature histories or unexpected combinations of faunal turnover and environmental change. In this sense, reading the long summer from the future is an ongoing process rather than a completed reconstruction. The Cretaceous thermal maximum stands in the geological record as a sustained exploration of one side of Earth's climate capacity, a world without large ice sheets, with high seas and warm poles, with forests at high latitudes and heavily stratified oceans. It demonstrates that life can adapt to such conditions in diverse and sometimes surprising ways, while also showing that the configuration of ecosystems under these conditions is distinct from cooler times. For present-day observers, it functions less as a strict analogue, and more as a distant mirror that reflects what a high greenhouse world can look like when given long periods to adjust. The mirror is not perfectly clear. Some lines in the reflected image are sharp, others are blurred or interrupted. Within those gaps, open questions remain about how often planets reach such states, how they leave them, and how living systems both shape and are shaped by the physics that governs their worlds.